Questions about anything?
Other complex matrices? Do we care about those at all in this class?
Complex matrices?
Yeah.
Occasionally. Mostly 2 by 2.
Okay.
Second question. Where is everybody?
It is the weekend of Labor Day. There's no class on Monday, by the way. Make sure. But if you ever have to miss class because of something like that, I post the videos of the lectures and the notes, so nothing to worry about. Let's see, at the end of last hour, I mentioned this basic estimate. It's a second kind of basic estimate for integrals. This is the complex version of integral of a complex function along a curve, dz. Well, anyway, that's a complex number, and the basic estimate is the modulus of that complex number is less than or equal to the max of the modulus of f along the curve times the length of the curve. And that's the actual length in R2. And the proof is simple. Remember, the definition of that symbol is it's an integral from a to b of the other kind of integral, f of z of t times z prime of t dt. You think of that z prime of t dt as being dz. That's how you remember the formula. So that's just by definition. And the modulus of that, the first basic estimate for that kind of integral was that modulus of that's less than or equal to the integral of the modulus of the thing inside. And if we can bound, of course, f is assumed to be continuous along the curve, so that integral is going to make sense. And since f of z, if f is continuous, then f of z of t would be continuous, and the modulus would be continuous, and that would have a maximum, call it m, along the curve as t ranges from a to b. That's the starting point and the ending point. And so that thing inside there is less than or equal to m, and therefore that integral would be less than or equal to m times the integral of the modulus of z prime of t dt. And remember, z prime of t is x prime plus I y prime. Where those are the that's a parameterization of the curve. And that modulus is the square root of x prime squared plus y prime squared, which you recognize as the formula for the length of a curve in R2. So in fact, that's the length. So this is less than or equal to this thing right here is equal to L, the length of gamma as a curve in R2. That's the classic formula you learn in Math 261. And so this is this whole thing is less than or equal to m times L. Check. So that's a very simple proof. It's just to write down and estimate. Questions about that? Well, today I'm going to prove the beautiful Goursat's lemma, which is one of the most beautiful, simple ideas of a proof in complex analysis you'll ever see. I'll need something. I'll call it an important fact. The integral around a closed curve of a polynomial is 0. If gamma is a closed curve, needs to be closed, and p is a polynomial. And so, you know, if this is true for polynomials, well, limits of power series are limits of polynomials. And so we'll expect this thing to also be true for power series. And power series are very related to analytic functions. So this is sort of a prelude to a big theorem that's coming called Cauchy's theorem about the integrals around a closed contour of an analytic function. So this is a polynomial. It's a complex polynomial. Well, it's an easy fact because z to the n is equal to a derivative of something. That's the integral. That's the derivative of 1 over n plus 1, z to the n plus 1. And so that means the integral of z to the n around a closed contour. And this is a fundamental theorem of calculus number 1 or 2, I forget what. So that's going to be equal to the integral of a derivative, d by dz, of this. And fundamental theorem of calculus, what was it, number 2 probably? Yeah, number 2 would tell you this is the thing, the inside, 1 over n plus 1, z to the n plus 1, between the start and the end. And of course, if it's a closed curve, the start and the end are the same thing. And so that is a big fat 0. Okay. In fact, the same argument works for negative powers. So a remark here. N equals n in z unequal to minus 1. Minus 1 is the tricky one. Minus 1 is like a log thing, and we're going to see it is a log thing later on. So works too. You got to be careful though. You better not have the origin in the curve for the negative powers. 0 not in trace gamma if n is less than 0. Same proof. Well, in particular, if something is analytic, then it's very well approximated by AZ plus B. So note, the integral around a closed contour of AC plus B is in particular is 0 when gamma is closed. And I'm thinking about this as being approximately equal to an f of z. So think that's approximately equal to f of z analytic locally. And that's Goursat's brilliant idea, is to use that fact in a clever way to get something fascinating. So let me state what Goursat's lemma is before I get rolling here. Goursat, the French mathematician, he wrote a big calculus book that everybody loved for a long time. So let's see, it's about an open, I've got omega in the complex plane, an open set. There's going to be a crazy 1 point floating along that I'll always be mentioning, but surprising how unimportant it is. A point P in there, and F, which is going to be analytic. Let's say, first of all, it's continuous on all of omega. And it's analytic on omega minus p, which is kind of a weird thing to do. And let's see, Q is a triangle. So here's a triangle. The triangle is going to include the boundary, and it's also going to include the inside. And that's going to be contained in omega. So the closure of that triangle is in omega. Well, then the conclusion. Here's an abusive notation. Q is equal to the triangle is equal to the boundary of the triangle the curve going around. I'm going to use the same Q for everything, just so I don't have to have so that's an abusive notation. But the big conclusion is that the integral around Q of f dz is equal to 0. And that's true even if P is inside the triangle or nowhere to be seen. Okay. So I guess I should draw a quick picture here. Here's omega. The picture, so there's the inside of omega. And the triangle, here's the triangle, Q. And P can be either inside that triangle or even on the boundary of that triangle or any old place. There it is. Of course, triangles have piecewise C1 boundaries, so they're the type of curves we've been studying. Well, the proof is going to be fiendishly clever and beautiful, one of my favorites. So let's do the case P is outside the triangle. And let's write Q sub 0 is equal to Q, the triangle. Okay, now Goursat cleverly started cutting this triangle up into smaller triangles. So here's Q sub 0. You take the midpoint of all the sides, and then you connect those midpoints and make triangles. Okay, and let's suppose our triangle is parametrized going around counterclockwise. Doesn't matter which way we do it, so it's going around like that. And if you look at that for a second, you realize something interesting. If I parameterize these things, let's see, I'm going to make this side go like that. And I'm going to make this side go like that. I'm making these triangles all go around counterclockwise. Then, if I do the opposite in the inner one, make it go like this, it would go the other way. And so that's the aha moment. If I parameterize all those triangles counterclockwise and add them up and realize the integrals around the cuts are going to cancel. Okay, so let's call this, I'm going to call these smaller triangles, I'll call this top one Q11, Q1 comma 1, Q1 comma 2. This one in the middle here is going to be Q1 comma 3, and this one over here is Q1 comma 4. So the aha moment that's going to make this interesting is that the integral around Q naught of f dz is equal to the sum, as j goes from 1 to 4, of the integrals around the smaller ones. Let's see, that's Q1 comma j of f dz. And that's because those little orange arrows are going opposite directions those are going to cancel when you end them up. Questions about that? And now I need a baby lemma. It's so baby that I feel embarrassed to prove it. A baby lemma is that if I have an integral like that, that's a sum of four things, at least one of those four things has to be big enough. So, if that's the case, then there exists a j with an aj at least big enough to make that f modulus bigger than or equal to the modulus of I over 4. So those are complex numbers. Okay, that's kind of a no-brainer. But if I made you sit down and write a formal proof, you'd realize the I equals 0 case. Well, the I equals 0 case is dumb. Right? Because, of course, it's bigger than or equal to... All four of them are bigger than or equal to 0. Check. So, what about the I unequal to 0 case?
Did you just say that I is less than 4 times the max?
What?
So I is equal to that. So
I is equal to that.
So then it's bounded by 4 times the max of A1, A2, 3, 4.
Yes. Yeah, that's basically the argument. So, if I is less than, let's see, that's not an if. I is, of course, less than or equal to by the triangle inequality, the sum of the AJs. And if they were all strictly less than I over 4, then that sum would be strictly less than I over 4. So this would be less than the sum of I over 4 if they're not. If they're all less than. And of course, that's a contradiction. Yeah, I always regret proving that because I make it sound like it's. Question?
The modulus of I is just the sum.
It's modulus I is less than or equal to the sum of them. That's the triangle inequality there. And if those were all less than I over 4, then of course that sum would be strictly less than I. And it can't be. It's equal to I. What am I saying? Yeah, I get that modulus I is strictly less than the modulus of I, and that's false. Okay, so that's enough of the baby lemma. So that means there exists one of those triangles where that integral is kind of big. So there exists a j, let's call it j1, such that. Did I say? Let me go back up here. I'm going to call this I. This is what I want to show is equal to 0. Okay, that's my integral. So there exists one of the triangles, J, such that the integral around Qj, let's see, Q1 comma J1, f dz is greater than or equal to I over 4, since they add up to I. So that's the big one. And eventually we're going to show that those get too big. Okay, so now the idea is to repeat this. Okay, so now I have a triangle. Let's say it's that middle one. Then it would look upside down. Let's say this is Q1, comma J1. Then I do the cutting. I take the midpoints again and cut this one up. And do the same business. And let's see, this would be Q2, 1, Q2, 2, Q2, 3. And there would be, well, maybe this would be a Q2, 4, the bottom one. And then this one in the middle would be a Q2, 3. And the same thing, they add up. And so one of them is going to be a big one. And I can do it again and again. So let's say then the next one is this one. Let's say one of those is going to be a bigger one. And then I'll do it again. And I'll keep doing it. Okay, so let's say I'm repeating it this one time. I get a Q2J2 with that integral being kind of big. So let's see, that would be integral of Q2 comma J2 of f dz would be greater than or equal to 1/4 times that previous integral, integral around Q1 comma J1 f dz. And that's greater than or equal to I over 4. Okay, so now I get I over 4 squared. And I keep repeating. And so what I get is a sequence. I get a sequence of triangles. Let's see, we started out with Q0 containing the Q1 was my first one. Let's see, I'm going to write Qn comma Jn. I keep getting the biggest one, and I'm going to call that Q sub n. I get a sequence like this. They're shrinking down. Dot, dot, dot. And that inequality is going to show me that the integral around the nth one of f dz, let's see, one time was a 4, 2 times was a 4 squared, n times is going to be a 4 to the n. Let's see, if I go back to this picture here, I'd pick one of the, let's see, so this, I'd pick maybe one of these, and then I'd do it again here. And so they keep, notice that they're contained in each other, and they're getting really small. Well, there's a famous topology lemma that if you ever took a topology class, you would have seen. About telescoping compact sets. So let's suppose that K sub n, they're not empty, are compact. Does everybody know what compact means? I hope. It means closed and bounded. It's equivalent to being closed and bounded. It also means every cover by open sets has a finite subcover. That's the real definition of compact in topology. And they're telescoping, meaning that K0 contains K1 contains K2, etc., then the conclusion of this lemma is that the intersection of those things is not empty. Of course, it's not true if they're open sets, but if they're compact sets, meaning closed and bounded, then it's true. And furthermore, if those diameters of those things, this is a metric space, so we can talk about diameters. Furthermore, if the diameters of those compact sets go to 0, then it's a unique point. Diameter of the KNs tend to 0 as n goes to infinity. Then the intersection is a single point. A single point in my original K0. Okay, I'm not going to prove that topology lemma, but it's an easy proof. And if you've had a topology class, you would have seen it. The triangle proof is particularly easy. Let's see, what the triangle proof is. I take a corner. Pick a corner. Pick a corner. Of each triangle. Let's see each triangle. So that would be, say, a Wn in my Qn. Then it's really easy to see that. So those are in. See each of those are in smaller and smaller triangles, and so they're getting close. So that it's easy to the diameters are going to 0, and so the fact that the diameters are going to 0 shows you that that's a Cauchy sequence. Wn is Cauchy. Because the distance between Wn minus Wm is less than the diameter of Q sub n when m is bigger than n. So it's a Cauchy sequence, and we know that the complex numbers are complete, so the Wn converge to something. And since Q0 is closed, so Z0 is in K0. In this case, I'm doing triangles, so I'll call it Q0. So that's all there is to that. So it's a very elementary proof for triangles. Okay, now back to the Goursat lemma. Let's write the intersection of all those Q's is equal to a single point Z0. I guess, yeah, since those diameters are going to 0, it's clear that can't be 2 points in that limit, because then the diameter would be eventually bigger than or equal to the distance between those 2 points, and it's going to 0. So there's only 1 point. Okay, so that Z0's in all the triangles. Okay. And so eventually the triangles are going to get really close to that Z0. And so if I realize that near Z0, since the function is analytic, that that z naught is not p, I can approximate it by a linear az plus b kind of function. And I'm going to show that the integral around those triangles is too big if they're bigger than or equal to that I over 4. So let's see. Near z naught, which by the way is unequal to p, I can write the difference quotient f of z minus f of z naught is over z minus z naught. That would be equal to f prime of z naught plus an error. Okay, and we know that e of z goes to 0 as z tends to z naught, because f is analytic there. And I'm going to define e of z naught to be equal to 0. Because when I do that, I can solve this for f of z and get that f of z is equal to f of z naught plus f prime times z naught times z minus z naught plus, we've seen this before, e of z times z minus z naught. Okay, this is like an az plus b kind of thing. And so the integral of that part around is going to be 0. Around any triangle around there. By the way, this thing is continuous because of my definition of the e. It's actually continuous on omega because of my e is defined up there, and if I define e of z naught equal to 0, that makes it everything continuous in there. And so now if I integrate, let's see, I guess I'm going to take let epsilon be bigger than 0 now. Let epsilon be bigger than 0. Those triangles are squishing down to z naught. So there would exist a delta such that, let's see, I need, I'm sorry, there exists a delta such that e of z is less than epsilon, since it's going to 0, when z minus z naught is less than delta. Delta is the distance I want to squeeze the triangles in. And so since our triangles are squishing down to z naught, there exists an n such that the nth triangle is contained in the disk of radius delta about z naught when n is bigger than capital N. Okay, so my function is going to be small there, and my triangles are squished into that disk that makes it small. I guess I should draw a picture. Here's my disk of radius delta about z naught. Z naught is in all my triangles, and so eventually the q sub n's get small enough so that they're stuck in here. That's the picture. Of course, Zn could be a corner, or it even could be on an edge. And those triangles only get smaller from that point on, so they telescope in. Okay, now I claim the integral around the Qn of f dz I had a formula for the f above there. Where is it? There's my f. So when I integrate that around, I'd get the b plus az part, which would integrate to 0. I get the integral of q sub n of b plus az dz, and that's going to integrate to 0, big fat 0. And then I get something that's going to be way too small. The e of z times something that's kind of small, z minus z naught dz, around a small triangle. So it's going to turn out to be way too small. So yeah, I'm anticipating that this is really small. Too small. Okay, so when I estimate that, using the basic estimate earlier I did at the beginning here, that's going to be less than or equal to the max of E of z times z is when z is in the trace of the gamma n triangle. In fact, it's just the boundary of the triangle, but what the heck, I'll stick in the whole thing. And then I'll get also the maximum of the z minus z naught when z is in the triangle. And then I'll get the length. So I'm abusing my notation pretty bad here. Qn stands for either triangles or boundary of triangles, or the length of the perimeter. Okay, so this one's, we know that the E is less than or equal to epsilon. In fact, it's less than epsilon. This, max, is less than or equal to the diameter of the Q sub n. And this is the length of the Q sub n. So think about the triangles. Every time I cut them in half. So what is this length here? The diameter of Qn is equal to, let's see, the diameter, they get cut in half every time. So that's 1 over 2 to the n times the diameter of my original. Q naught. Okay, so that's really small. My length is also 1 over 2 to the n. So this one is 1 over 2 to the n times the length of my first one. And so I get 1 over 4 to the n. So this is going to be less than or equal to 1 over 4 to the n epsilon times the diameter of my first triangle times the perimeter, the length of my first triangle. And that's, let's see, that's too small. Too small. Because I have this, remember I have my, it's too small because, remember I have I over 4, it was bigger, so that's less than or equal to the integral around Qn. And this one's less than or equal to oops, this is because this is 4 to the n. And I have this less than or equal to this something else, an epsilon. Times something. C. Let's call this thing C. Okay, and epsilon is arbitrary. So let's see, I can cancel out the 4 to the n's, and I get that I is less than or equal to c times epsilon. And c is a fixed thing. Epsilon bigger than 0 is totally arbitrary. So we see that I, the integral, has to be 0. So that's fiendishly clever on Goursat's part. I think you'll have to go back and draw that picture and think about it yourself, just so it starts sinking in, because it's kind of an intricate argument, but it's very elementary. And it's just analytic geometry to check that those diameters and perimeters get cut in half every time. That's a pretty easy thing to believe. Questions about that? Yeah.
Sorry.
Yes.
Are there any other shapes other than triangle?
Yes. Every shape you can think of. But triangles have a particularly easy way of some books like to do it with rectangles. It's fairly straightforward in that case, too. You'll see why I like triangles when I do a difference quotient soon. Did you have a question?
Yes. So I was curious, for this lemma, what's stopping us from just using, like, as if f is continuous and analytic and it's nice and all that, what's stopping us from just using the fundamental theorem of calculus and then just going across the triangle and then eventually it just...
I don't think... You're going to run into issues there, I think, because you can't really use Green's theorem yet, because we don't know the derivative is continuous. But even that's part of that little paper I wrote. You might want to read, because questions like that are addressed. But this is clever, and I don't. Yeah, if you can make that work, come and show me. The paper I put on the bottom of the home page that I wrote, an expository paper about the cleanest, quickest way to get some of these facts. Well, let's see. That takes care of the case of P not in the triangle. Now I need to do the case of P in the triangle. And so first I'll do the case P equal a vertex. Okay, so here's my triangle, and my P is going to be a vertex. And the clever thing to do here, if P is a vertex, is to cut the triangle into a little tiny triangle near the vertex, and then make this triangle, and then do the usual routine. Integral around my Q is equal to a sum. Okay, the integral around the triangles that don't have a P in them, we know are equal to 0. So that's going to be equal to the integral around the tiny top triangle, or corner triangle. And of course, F is continuous there, so it would be locally bounded. Continuous at P. So mod F is less than or equal to something near there. And so you'd get that the integral of F around that tiny one is less than or equal to m times the distance, times the length of the tiny one, which of course is tiny. And so that can be made as small as I want. So that can be made arbitrarily small. Okay, so that's easy. Questions about that? I love these sneaky arguments where you don't have to do anything. Next case would be P being not a vertex, but a key. P in a side, an edge. Okay, then I'd have my P like this, on an edge, and I would take I cut it into two triangles and see that the integral around this Q would be the integral of sum of 2. I do the going around counterclockwise, and you'd see they cancel again. I didn't do that in the last time because I guess we saw that picture. But if I did it going around counterclockwise, they'd cancel along that blue line, and I'd see that this is the sum of 2. Whoops! What did I do? I don't know what I'm doing. There it is. Sum of 2, and they both have the vertex in the corner. The vertex case. I've reduced it to the vertex case. So check. And then finally the P equal the inside case. So P would be somewhere in the middle. And then what would I do? It's easy to make triangles out of that. I would go like that. And add them up going counterclockwise, and they cancel on the blue stuff, and I'd see that I'd reduced it to P equal vertex case again. So that's the end of it. Let's see. I got 2 minutes now. I throw 3 minutes. Why the P? Why care about P? We're going to get the Cauchy integral formula. And so it's because the difference quotient, f of z minus f of z naught over z minus z naught minus z, is continuous up to z naught, because it tends to f prime of z naught as z tends to z naught, so it's continuous there. And this is analytic away from z naught, if f is analytic. So when I apply the Cauchy-Goursat theorem to a difference quotient, it's going to spit out something pretty interesting. And in fact, I'm going to use it when I prove the Cauchy integral formula. And this will be important when we prove the Cauchy integral formula. Which is a famous thing they'll soon get to. Any last minute questions about anything? So I posted homework 2 on the home page. I'll soon get it into the Gradescope also. Anybody have trouble with Gradescope? I figure you've used that before. Any last minute questions about anything? Well, have a good Labor Day weekend.
Due today, right? And then you're like, then I checked after that. I'm like, oh.
Although we may not need it, but it doesn't matter if we have just one such P or
Yeah, you could have.
finite number.
This is why we only care about one of them, because we can do it in this case. But yeah, there could be finitely many.